I'm really excited about these results, but I think it also opens up more questions than it answers. It's like we're getting hints of truth, and so now there's like, oh, so many good things to follow up on. So worth the discussion. Uh, Let me see here for sharing the view. Uh, what do I want to do? Slideshow? Yeah. Sorry, this should be second nature. Uh, Great, you can see it, right?
Yep.
Cool. Um, okay, so I will share this work that we've been doing for, I think it's been kind of in development for 2 years or something now, depending on where you draw the boundaries, about transformers learning factored representations that effectively transformers and other neural networks, they're learning to factor the world into parts. You get a monolithic kind of stream of data. You can imagine this happens for transformers getting streams of tokens, but you could also tell this story about us or really any type of agent where you just have a stream of inputs. And how is it that we ever come to know the world, that we ever come to see, this is a tree, this is a coffee mug, this is another agent acting in the world. I think it's really easy to take for granted, but it's pretty mysterious actually of like why why and how we would partition the world, naturally at its joints or otherwise. So this works on Archive now and was a huge collaboration with many good folks, including Alec and Kyle, who are here. So you guys can also set me straight if I stumble and say something wrong. Um, and as I have alluded to already, there's a set of specific results, but for me, it's already done this big work philosophically. So an alternative title, which maybe is what I really hope to convey, is something about reductionism and belief in a complex world, that there's this geometric imperative. And um, I think maybe I'll just not say too much more on that at the moment. Okay, so from a stream of data, how and why do we partition our world into parts? So you could imagine yourself, you're getting a stream of visual input, some auditory input. Again, for a transformer, you're getting a stream of tokens. You can just imagine like a sequence of numbers. And, even if it did factor the world into parts, should it? Because there's some idea from maybe Eastern philosophy that actually it's better in some way. It's more enlightened to see the world holistically. So why wouldn't we just see the world as it is, that we're all part of one big thing? Um, so it'll turn out that, to give a bit of the punchline, there's this exponential dimensional advantage to factoring the world into parts. Uh, but that was not at all obvious to me, maybe obvious to you guys. I actually would be curious, even at this point, to get people's thoughts on this, like holism versus partitioning of the world. If there are like other things that either feel obvious or questionable, or you would wonder about universality.
My first thought about holism versus parts is, from a physics perspective, which is, we often view the universe from a theoretical physics perspective as one big thing evolving unitarily,
Mhm.
right? And what is the meaning to say like this is me, this is my environment? It seems kind of arbitrary. And I think that's one of the big mysteries is like, how do you identify an observer within this big unitary evolution? Like, how do you say this is what's doing the measurement? This is what's doing the control. That's a big mystery, I'd say, in physics generally. So I think
Yeah.
this question is not limited to um, artificial intelligence.
Right. Agreed. I think a lot of our work's been done on transformer models. We also found that it's effectively the stories unchanged for RNNs and other type of neural network architectures. And it's also a problem for us, or a problem or opportunity or a question. Um, yeah, something that this has brought to mind for me is when we, maybe especially when we're doing quantum information type physics, we'll write down the Hamiltonian, and for multipartite systems, we'll write down, okay, the Hilbert space has this tensor product structure. Well, where does that come from? I mean, it's just written at the beginning of the paper. There's like a system and an environment. So you have like the the vector space for the system tensored with the vector space for the environment, or maybe you have many subsystems. And where does that come from besides maybe some intuitive notion? There is a really nice paper by, I'm forgetting the first author, but it was in Seth Lloyd's group, where they talk about um, kind of the arbitrariness of the tensor product decomposition of Hilbert space, which is like how we think of breaking the world into parts. It's not just a choice of basis. It is what is a thing and what is not a thing. Um, they kind of talk about the arbitrariness about it, but in the end suggest that the natural decomposition is according to those things that we can act upon. Um, so that's pretty neat. And maybe this is an extra question to this. If transformers are just observing tokens, they're not acting upon anything. So there's a further part of the story. If they are factoring the world, there's a bit more to just than just that.
Yeah, I think you've mentioned this paper before, and I've honestly not read it, but I think it's a
I think it's
fascinating
bizarre.
idea to challenge not just the assumption of the basis that we're living in, but the separation of our the way that we separate our world into different bases, or sorry, different Hilbert spaces. In general, I think it's good to like identify the different assumptions that are going into the results that we assume or the results that we derive. Like,
And I don't know. Can you guys hear me still?
Yeah.
Yeah.
Cool. Okay. So just to jump in here with the kind of the mystery question of
Mhm.
when you look at things from a theoretical perspective, you think, wow, there's this giant unified Hamiltonian that's controlling everything. How do we know how to break it up?
Mm.
And it seems mysterious in theory until you start thinking about practically almost no, like zero part of that Hamiltonian has to do with any particular thing, right? So if I want to predict what's happening to me right now driving in my car, I care about such a small fraction. And even for that small fraction I care about, I only care about their kind of average placement and the way they're affecting my car right now. And so, in a practical way, the mystery is how could we even look at this thing as one unified thing as far as I'm considered? And the factoring thing is actually quite natural.
Yeah, that's an interesting point of like just knowing the world, it would maybe obviously be so impractical to track everything.
It makes me think of Alex's causal states. You know, she has this algorithm that learns causal states from like a larger kind of essentially tensored Hilbert space. You know, it figures out what are the subcomponents. And the other thing it made me think about is if you like attach the two fingers of a monkey's fingers together so that they always get information together and they always move together, then like the map in the brain of those two fingers converges into one map. And so it does seem like, and the thing about acting on what can we act on,
Mm.
like that's what makes a thing is that it does when you push on it, it moves, you know, it accelerates or whatever. If it's a rigid body, then it's all one thing. It doesn't matter that it's really made of other smaller things.
Yeah. Yeah, it's also interesting in terms of the division between like um us, me as a part versus like me versus other, what we consider in that boundary. With the monkey thing, the poor monkey, but it's like, does it end up only learning like it can only move them together in the end?
I think that they like attach them together like surgically or something, and then the maps converged in the brain, and then they like unattached it, and then it like eventually learned how to like remove them separately, and the maps re-diverged in their brains. Some kind of a brain imaging study.
Yeah. Yeah, actually, if you have that paper handy, if you could forward that to me later, that would
No, it's a thing I read many, many
Oh,
years
okay.
ago, but
Yeah. Okay. Uh, Fascinating. Slightly cool, but fascinating. Um, okay, so I'll, in the interest of time, carry on here. But yeah, I think all of these different angles at it are really useful and nice. So, okay, so let me get a bit into the way that we've chosen to formalize the problem, because it maybe feels so big as to be daunting. So let's say that there's some ground truth for what the world is, that we are going to be training a transformer on, and we're going to take an example of a generalized hidden Markov model for the data generator. This is actually very general in that it includes nice toy examples of hidden Markov models, but it also includes things like repeated interactions with quantum systems. You can imagine, if you want to get a quantum system in this framework, a natural way to do that is something like, you think of vectorizing a density matrix, and then you can think of your Krauss operators are usually usually those things act via some superoperator, and either just working as some linear operator, and then POVMs end up giving you an observation, which is like a token X, and they also move the system forward. So this is a quite general setup. We'll be typically considering finite dimensional things. So the historical context is important here. So we're going to think of like discrete time tokens coming in. So this X1 through L is just saying a sequence of tokens, a realization of a token sequence. You can think of from time 1 through time L, X1, X2, and so on, F through XL. And then the hidden structure that when we are building ground truth to see what happens, um, there's a hidden structure that we impart to this world, where actually every token, every X, every symbol, happens to be generated by n latent processes that are running in parallel, that they may or may not be affecting each other. And it's kind of in coordination that a token is chosen. And so in this setting, the question is, okay, will the neural network kind of back out and figure out, oh, this world was made of parts or not? There's nothing a priori that the model would see that would say the world has n parts. It's just a stream of tokens, but the way that we know that the way it was generated was by these parts. So a little more concretely, I'll gesture at some of this stuff, and then we'll come back to it more formally. But let me gesture at it first with some diagrams. So you could imagine, if you're trying to talk about a generator of sequential data with latent structure, we can think of these GHMMs, or let's just think of hidden Markov models. Then we can think about a state transition diagram. You don't directly get to see the hidden states, they're hidden. But if you were in, or if the machine was in any of these hidden states, there's a probability distribution of going to all the other states and emitting some observable token. So in this case, A's, B's, C's, and D's are um, rather, what do we have here? C's, B's, and D's? Do we have A's? Maybe just C's, B's, and D's are the observable tokens. Okay. In this case, the world, this very simple world, happened to be composed of two parts. We can imagine having HMMs that are effectively acting in serial. Let's just say in this case that they're totally independent. And then maybe what you observe is for every pair of possible outputs from each of the parts, there's a new token that that maps to. So maybe this is just kind of the simplest way of it's composing things without revealing that they're made of parts a priori. So you can say like 0, 0 maps to A, 0, 1 maps to B, 1, 0 maps to C, and 1, 1 maps to D, right? So you can imagine the data being generated either by this thing giving the binary sequences in parallel, and then those have some further operation to produce the C's, B's, and D's, or you could think of there's a minimal monolithic model, which is generally much bigger. In fact, the minimal GHMM, when you have many parts, grows exponentially in the number of parts. So the number of latent states grows exponentially in the number of parts. And what does that have to do with, okay, this is something generating sequential data. And if we're observing this, we are a transformer observing this, how do we represent the world? Well, if we're trying to predict, which transformers certainly are trained to do, famously next token prediction, given some historical context, what's the probability distribution over the next token? Well, to do the best possible thing at that, without even diving into any math, you can just say, well, the best possible thing I could do is to uh, figure out a world model. So say, aha, I figured out that this joint HMM produces the tokens in the world. And if I somehow figured that out, and then as I observe more tokens, even after training, as I observe more tokens, I update my probability distribution over the latent states of the generative world model. Then that gives me a probability density over all possible futures, the conditioning on that history. And that's the best I could possibly do. So that is a strategy that works. And if you think about probability distributions over the latent states of the generator, here there's 4 hidden states. And so I can think of the 3 simplex of probability distributions over those 4 states. So that's a 3-dimensional object. And there also happens to be this submanifold within those, which are product states. If you happen to recognize that the world is made of these parts, then in certain cases you see on this product state manifold. And if you recognize the factoring, actually this is just this, in this case, this 2-dimensional structure rather than this 3-dimensional structure, and so your beliefs could be represented in fewer dimensions. The bigger mathematical story that we'll get into shows that whenever you're on this product state manifold, which implies conditional independence among the parts induced by history. There's conditional independence induced by history. The dimension of the joint space grows exponentially. The intrinsic dimension of the manifold grows only linearly with a number of parts. However, the linear span fills up the entire exponentially large space. And then if you just realize you're on this low dimensional manifold, you can just like represent things in orthogonal subspaces and get away with this much smaller representation. So Alec.
Thanks, Paul. I just wanted to make the point that these dots that you put in this space, either on the left or the right, are sort of the minimal and necessary predictive states of the process, right? Like this is what you must store.
Yes, if
In
you're
both cases.
if you're predicting as well as possible, then you must be tracking these different beliefs. That's right. Thanks for pointing that out.
In some fashion.
In some fashion, yeah. The geometry of it maybe didn't need to be this way. Maybe you could have a dimension for each one or something.
Right.
But then there are these natural candidate geometries for how you would embed these predictions relative to each other.
Yeah.
And
And
then the non-orthogonality has to do with paths that induce similar predictions about the future. You can encode that by similarity, like cosine similarity, effectively.
right. And just for some further context, like
Mhm.
the on the left side, this is sort of the object that we imagined as sort of this fundamental predictive geometry for some time, these mixed states of the generative model. Um, and this is what you were finding in the before this work, this was what you were finding in the residual stream of transformers. You found that these belief states were embedded linearly in the mind of the transformer, right?
Yeah, exactly.
And what's surprising is that actually for these product states, you can reduce the dimensionality going from left to right.
Yeah, that's right. Um, so there's this kind of backstory, which I have a few slides on actually, but it's the backstory is we were finding effectively something like the geometry on the left in this joint space that the model's learning to represent beliefs and effectively do Bayesian updating in context of a minimal generative structure, like this thing in the top left.
Oh,
And then
sorry for
we're
jumping ahead
no,
on
no,
your
no.
slide.
It's really useful. It's a good time for that context. Um, and yeah, a major question is like, that's cute. Does this extrapolate to large models? Is this going to tell us something about intelligence at large? And one of the um, challenges to that is like, what if this, if the minimal generative structure for the world is blowing up exponentially in this case, then how can this possibly extrapolate? And what we end up finding in this work is that there's this sneaky trick called reductionism, where you can recognize that the world is made of parts and update your beliefs over those things in parallel. So I'll give a little bit more of the story here that that's a cute trick when you can get away with it, but you can't always get away with it actually if you want to do optimal prediction, because sometimes there are unexplained correlations among parts of the world. Even when you condition on everything you've seen, you're like, I noticed that these things are correlated. Maybe there's some feedback mechanisms. And so there is a push towards holistic representation if you really want to track all the correlations in the world. But if you do that, then it would be a lossy projection down to this factored representation. So now we see this tension between representing the world in this reduced way, which allows for a simple description of the world, versus representing the world holistically, requiring many dimensions. So this kind of simplicity of factoring versus fidelity of this joint representation. And I think I've probably said many times now, there's this exponential savings in the number of dimensions that an intelligent system would require to represent this. Okay, intelligent system, this is really just anything storing their memories in this real vector space. Um, Exponentially many dimensions in the joint case and linearly in the factor. So the experimental approach we gave um, is we generated the training sequences by some number of factors, some parts of the world. So let's say this is examples of ternary systems. So some of you guys know the MES3 process, which is a three-state HMM. There's also this quantum process, which can be generated by a single qubit. There's no finite HMM, but a single qubit and repeated measurements on a single qubit will produce tokens from 0 through 4. And so we take these 5 processes, they're all spitting out tokens in parallel, and then the tokens we train on are then whoops, uh, these numbers, which you can end up obtaining via effectively for every possible combination of the outcomes of all the factors, there's a unique token. That's how we're doing it in this case. So all of the information about the factors is contained in the tokens, but but the tokens are just numbers. So there's nothing in 424 or 36 that would a priori indicate there were 5 parts of this world that would lend a simple description. If you did belief updating, if you discovered that there's 5 parts of the world and you did belief updating over each one individually, you end up getting these beautiful geometries. So there's these theoretical factor geometries that is kind of the ground truth where every context would induce effectively a point on each of the factors. And here's the experimental bit of this. You train a transformer, every context induces some point in the context embedding space, just like the activation space of the model. You put in some context, and then there's just some state inside the model. So every context maps to some point, and you can check for the many different contexts, how do those different embeddings of the context relate to each other? There's some geometric relationship. And the main unsupervised thing people would do is just do principal component analysis. You look at the top few PCs, see if there's any obvious structure there. And you can also look at the cumulative explained variance, how much, which is effectively saying how much of the variation of the data, how much of the spread of the data is contained in the top, say, 2 dimensions, 3 dimensions, 10 dimensions, and so on. So effectively, how much of the representation space is being used up by the model? Effectively, how many dimensions? And then there's this other part kind of jumping ahead of that we expect if the model is factoring the world, then the ansatz here is that the model will be using orthogonal multidimensional subspaces. So orthogonal subspaces to represent each part of the world and beliefs over that. In which case, there you could imagine there's something like a linear map from the large activation space in the model to a low dimensional space for each factor. So this is kind of a sketch of what our experiments looked like.
Can I ask, I didn't quite get what's the relationship between the principal component analysis and the factors? Like, would the principal component also be the factor that's most important? Are they like completely different?
Sometimes the experiments are kind to us, and then it turns out like, oh, the first factor is represented in the first 2 PCs and the second factor in the next 2 PCs or something like that. It basically turns out that sometimes the representations aren't exactly aligned with the principal vector basis, but regardless, the top principal components do effectively tell us what the what the relevant subspaces are, where the factors live, and then occasionally we had to do more work to identify what the relevant subspaces were. When we know ground truth, we can just do linear regression to see where they are. But if we don't know ground truth, if we think the story extrapolates, then there's a bigger question of how do we do unsupervised discovery of what the parts are. It's a bigger question than we address here, but PCA gets you pretty far. It turns out that ICA, independent component analysis, works pretty well if you have independent parts. But there's other clever things still to work through.
Okay, thanks.
Yeah. Okay, and then okay, so here's then this interesting part that even when the ground truth of the world, so then we change the experiments a bit where maybe the world almost factors, but actually you need to be in this joint space for best fidelity of your predictions. Even in those cases, there seems to be kind of this attractor of the representation in the trained models that the models want to, or in any case, tend to learn factored representations for a long time, until you really push down loss. You say, no, this representation isn't good enough. And then finally it'll start popping up to use more dimensions. But there seems to be this inductive bias to ignore complexity in the world if you can get away with predicting the world pretty well in terms of parts. So um, I have I have slides for backing up to be like, okay, we've kind of given the high level story. I have slides that are backing up to be like, whoa, whoa, how are we anticipating these geometric representations in the first place? So I have some slides on that. And then I also have slides diving back into the math for this work. And just looking at the time, 9:40-ish, I'm wondering, Alec, what you think I should plan for?
Why why don't you give like a bigger picture to start off?
Mhm.
And we'll see how far we go. I think, we can go a little bit over time.
Mhm.
We started a little bit late,
And
but
we might need a part two.
yeah, we
Okay.
might need a part two.
Okay.
Yeah.
Then I'll just kind of go ahead with this and we can, there will be some natural places to stop if we want. But um, but yeah, hopefully it's useful and interesting to give a bit more of context of, okay, there's these fractal geometry things. Uh, what the heck? How are we finding them? And what's the backstory? So I'll say a bit of that. In the interpretability community, in the last year, there's been some excitement about activation geometry, that people are finding geometric patterns in large language models and other neural networks. Um, but they're finding them. They're not anticipating what they should be, but you'll find in trained models, you'll find things like days of the week end up being represented on a circle inside of activation space and months of the year also. And there's these other multi-dimensional embeddings that people are, wow, this is really curious. And then the work that we've been up to, mostly through Simplex, has shown that yeah, there should be these multi-dimensional features, and we can actually anticipate a lot of what they should be. And it has to do with developing something like a world model, and not only that, but also effectively doing Bayesian updating over the latent states of that world model during inference as it's observing more context. So just kind of a prelude to all this. So there's the story of transformers and belief updating, which is now very like core to my thinking, but I think not so core to um, to most people's thinking here. Um, Maybe in this group, but not outside of this group so much. Um, you can already anticipate the need for this, though, even at a behavioral level. So it's a little funny to me. It's not more natural. So um, performing well on next token prediction implies behaviorally that you need to be consistent with Bayesian updating over a world model. And this is after training, again, that you're doing Bayesian updating as more context is observed. I can sketch this out very quickly. Um, Basically, you can imagine any deep neural network as the layers are going vertically. Um, Context, you can think of effectively like time or sequential order of the tokens is going horizontally, x1 through xl. And every node in this, basically every vertex in this simple diagram is like a context position and a layer in the network. And this grid can be surprisingly useful, I think, if used well. Um, so anyway, at the end of, so the model has like some number of kind of hidden latent representation space. And then at the end, whatever the weight setting of the model, the weights and biases end up being some parameter vector, let's call it theta. And then there's some probability distribution um, induced by that weight setting. So the probability distribution over the next token here, x3, given the history, say x1 to 2, induced by that weight setting. So this is true at any point. Like even at initialization, there is some probability distribution over the tokens. So there are at least these two different distributions we want to think of. One is just whatever the model does at the weight setting. So that's like probability induced by theta. the parameters. And then there's this other like ground truth distribution over tokens, what I'm calling Q, which is what is the world that we're sampling sequences from. So you can think of, in any case, sequences are sampled from some ground truth distribution that maybe that's changing over time, whatever. But there's some, you can think of there's some ground truth Q distribution over token sequences. As the model is trained on next token prediction, it's effectively cross entropy loss. If you think of the expectation value over the ground truth sequences, the best that the model can do is tweak its parameters such that the predicted probabilities coincide with the ground truth. So for those of us familiar with computational mechanics, we see that, oh, the loss will actually depend on the context position, even at the end of training. And the minimal loss will look like the myopic entropy rate, which is the entropy of the next token if you condition as well as possible on history. So from that already, we should anticipate something like in context learning, that if the model does a good job, it'll use its context to reduce loss in context. So it's just a very simple version of that. And we wrote this paper basically to frame this in, I think, a natural computational mechanics way, that over the course of training, models do this thing, which is effectively Bayesian updating over a world model. You can just look at the in-context loss going down to this myopic entropy curve. And you can see on the left, there are like the ground truth generators that we used. In the middle with the green states, there's the optimal Bayesian updating you would do over those states. You can think of that as also a graphical model. And then the implication would be the best possible predictions. Okay, so behaviorally that works out. But how about internally? Does the model actually have a representation, a world model that would seem to be an open question? That's something that we've worked on a lot and have shown that at least in many, many simple cases, this turns out to be true, and it seems to extrapolate pretty well. So this was the subject of our NeurIPS 2024 paper, where we trained on this three-state hidden Markov model called MS3. If you trained a model on that, you might say, what's inside? If it learned a world model, maybe it learns transition parameters. Instead, we anticipate this kind of crazy fractal, the theoretical prediction here, which has to do with, again, this Bayesian updating. Different contexts are embedded non-orthogonally relative to each other if they make similar predictions about the future. And then as you train for longer, indeed, the model's weights rearrange such that the contexts are embedded relative to each other according to the structure. So again, every point here has to do with a particular context, and the points relative to each other is how they embed relative to each other. Right? Okay. To be very concrete, when we use hidden Markov models, you can think of hidden Markov models are a way to produce tokens. It's a nice ground truth setting to test and falsify various hypotheses about representations. The great thing about HMMs is that you can generate sequences where you can effectively calculate sequence probabilities according to linear algebra. So there's some initial vector for HMMs that's going to be an initial probability distribution over the latent states, so eta nothing. And then there's matrix multiplication of these labeled transition matrices, TX1 through TXL. And then the ones vector here is just accumulating probability, integrating probability. So the ground truth probability of some sequence x1 through L can be calculated by linear algebra. That's great. And in fact, if you just if all you want is the linear algebra, that's one of these generalized hidden markup models, JHMMs. You could imagine, again, this looks like quantum in that quantum is linear. Maybe hidden linear because you don't get to see the density matrix directly. You have to do POVMs. So, okay, we can take these types of generative structures, take any of these generalized hidden markup models where you have probability distributions from linear algebra, and then where's all this geometry coming from? You can see it fall out immediately just from the linear algebra, where the probability distribution over some future, so this is big X with a right arrow over it, given some particular history, this is little x with some left arrow over it. Well, if we can calculate that by linear algebra, that's just the probability of the joint history x and future big X divided by the marginal of the history, right? So this is just writing down the linear algebra probability of the joint divided by probability of the marginal. But now when you write it down this way, you can group things as I've suggestively done here on the left, that the historical context, the only thing it does is to induce this vector that we call a predictive vector. And any two contexts that induce the same predictive vector cannot affect the future differently. And moreover, any two contexts that induce nearby predictive vectors cannot affect the future very differently, right? So there's something about already a natural embedding and what geometry and geometric relationships mean if we were using such a model and updating according to such a model. So for that reason, it turns out that these predictive vectors, these etas indexed by the word that induces them, these are the things that matter. These are sufficient statistics for predicting the future as well as possible. And how do we think about that? Well, we can think of there's some generative structure, like this thing on the left. Then there's some metadynamic for how your beliefs evolve. You can think of that also as this is like an explicit graphical structure of how you move from one eta to another, from one predictive state to another. It's not always the case that the recurrent thing looks like the generative thing, but it just is in this case. And okay, but each of these, we can call them belief states or predictive states. Each of these etas are just, in the HMM case, they're distributions over the latent states of the generator, so they have a natural geometric embedding. So each of these belief states is just a probability distribution over the latence of the generator. So they have this natural embedding, and in the three simplex, you say, think of like probability of the first state, probability of the second state, probability of the third state, and probability is normalized, so you're restricted to this probability simplex. So if you embed all the states that way, there's some geometry, and then we indeed find that that's how transformers are modeling the world. So cartoon of a transformer is you have repeated layers of attention and MLP, multi-layer perceptron, feed-forward network, whatever you want to call it. Every context gets embedded into the high-dimensional activation space. And the ansatz, the thing that we find is then there's a linear map from the high-dimensional embedding to just the simple belief geometry. And initially we were doing linear regression to find this, but it turns out you can just do PCA and you can find this stuff in the top few principal components. So this was the lesson of that early work. And since then, there's been a number of other works that we've figured out, okay, how do transformers do this apparently recursive updating if they're feed forward? And investigating that, we found mechanisms of how that works out. We can anticipate geometries that are developed at earlier layers, and so there's all this beautiful stuff. Okay. Okay, now you, an esteemed scientist, are listening to all this, thinking through it, and your object of study, this inscrutable set of matrices that we call a neural network, maybe is giving way to interpretability. Okay. So you're thinking now that Simplex has been saying, okay, predicting the next token well means that you perform Bayesian updating over the latent states of a generative world model as you observe more context during inference. You're thinking, okay, I'm getting this. So we're talking like hidden Markov models, that's the data generator, or should we be talking about Boolean circuits, Turing machines? Surely you're not talking about quantum computing. Like, what's the type of world model we should be thinking about? Um, and we're going to come back at you and say, well, actually, quantum computation is a pretty good model. It's actually um, the type of world model is much more similar to quantum computation than you might think otherwise, because the models, neural networks are actually using the real vector space to embed memories. And a lot of the nominal advantages of quantum computing is that um, qubits and quantum states uh, live in this real vector space, that they can use the continuity of the vector space to have certain advantages.
Real vector space?
Real vector space. So despite using complex numbers in quantum mechanics, density matrices are elements of a real vector space. And how do we know that? Well, uh, let's say eigenvalues of a density matrix end up being probabilities that all sum to one. And now if you want to take uh, linear combinations of density matrices to stay in the space of density matrices, then you must take only real combinations of those density matrices. Otherwise, you would no longer be in the space of density matrices. So if you think of a density matrix as an abstract vector, they are elements of a real vector space. And to stay inside of that, you have like real coefficients that weight them and move you around to different density matrices. Yeah, so the fact that we use complex numbers in quantum mechanics is just like this representational convenience, or maybe it's a representational confusion. I don't know, but it's kind of an interesting thing.
That's bold.
It's a good time to be bold.
Can I just ask, can I represent every superposition of quantum states as a superposition of density matrices?
I would say that so if we're thinking about a density matrix on a well, yeah, forget joint space. So for superposition, we're talking about there's some preferred basis, and then you have coherence in that basis. And so having superposition is akin to having a non-diagonal density matrix, right?
Yeah, but if I start with, I'm just trying to decide if I can get everywhere I can get if I only use density matrices and linear superpositions of them,
Right.
as if I started with.
Yeah. Yes,
States.
if you consider, because right now we're saying we just care about the space of density matrices, and if you consider all extremal states, these are like pure states are extremal states in
Sure.
the quantum setting.
I can definitely get
And-
all pure states. My
and
question
then-
is, can I get any arbitrary?
Yeah. So
Position.
then the convex hull of all of the pure states give you all possible density matrices. And the convex hull is just convex combinations. So those are just real numbers weighting all of the pure states.
Yeah.
Sorry, Paul, I'm not to get stuck here, but okay, just take a qubit.
Yeah.
There's a continuum of pure states.
Yes.
And somehow the every state, how many
Yeah, how many
What's the
density
convex hull? You're
matrices?
saying like the entire outer rim is the convex hull, and each of those
Mm.
elements is uh, representing, a basis element in our real vector space?
So this is a great segue to this next part here.
Okay.
But to address that specifically, you can think of for a single qubit, you have the block sphere where all the different points on the block sphere tell you all of the different truly distinct um, uh, pure states of a qubit. You could have in the computational basis, you could have the zero state, you could have the one state. In pop culture, people say zero and one, but it's really annoying because you could have zero plus one or zero minus one. The actual combination matters, and you could have everything in between. Um, but we know, of course, that a basis for qubits is just this two-dimensional thing. Like zero and one is a sufficient basis, plus and minus is a sufficient basis. But then linear combinations of pure states take you to different pure states. Okay, so this is admittedly this confusing thing that there are two different types of linear combinations. There are linear combinations of pure states as um, uh, like not density matrices, but like as these vectors, which take you to other pure states. And then there are linear combinations of density matrices, uh, which which you can consider the convex combination of those is the convex hull, which is the interior of the block ball. Um, right.
But how
So
many density matrices do you need? Like if I want a
hmm,
basis and I'm using kets, then I just have I have zero and one or have minus
yeah,
and
yeah.
plus. But if I want to use density matrices and I want to get anywhere on the
Mm,
surface and on the interior,
yeah,
my
yeah. Then
my
yeah, I think
state space is infinite now, right?
um yeah, I get your point. It's a good point that um there are infinitely many density matrices that are extremal states. And um you would need to effectively enumerate all of those if you want to get all possible linear combinations. Um, but I think there's an alternative way of thinking about it that I'm advocating for that like that is true, and it is still also true that that all of those density matrices just live in a two-dimensional well, for a qubit, a three-dimensional real vector space.
Maybe
It's
we can get into the details of the quantum at some point. I think that would
Mhm.
be maybe a nice follow-up, uh,
Yeah.
like where we really delve into like, okay, if we vectorize this thing, what are POVMs doing? Is it real? Is it complex? Because I like when I see this, I think, okay, let's look at the A form, the vectorized form, and then that's going to be a four-dimensional basis. But I
Mhm.
don't at this point, I'm not sure how that all plays out.
Yeah, and in fact, when we're looking at the block sphere, we are implicitly looking at some vectorized form, in particular the block, the block vector.
Mhm.
It is a vectorization of the density matrix. There are other ways of vectorizing it. There's A form and other things. Um, but they're actually all linearly related to each other. There's a linear map from density matrices to block matrices to other representations. Um, and so yeah, it's super interesting. There's like a lot to go into here. And I
So
think
I want to be
Emily,
cognizant that we're at like 5 minutes over the hour, maybe
yeah,
like 5, 10 more minutes, and
yeah, that
then
sounds good. Let me find a natural place to wrap up here. Um, so but yeah, Emily, I think you're touching on a important and nuanced point here that we can choose to think about the space of density matrices, but maybe now there's this burden of finding the boundaries requires infinitely many, well, there are just infinitely many extremal points. And so if we choose to focus on density matrices, um, then finding all those extremal points feels non-trivial from density matrices themselves. So there are a few things that are simultaneously true, and I think it's just useful to keep in mind.
One thing, sorry to
Mhm.
belabor this point. I think since you're operating in the GHMM context, though,
Mhm. Mhm.
I think the pure states, the relevance of the pure states is no longer so critical because if you have like a classical GHMM, you can go outside of the simplex.
Uh, yeah, so one of the things I wanted to point to here is what what is the relationship between these predictive vectors, belief states, when you have an HMM, a quantum system, or for a GHMM, it turns out corresponding to one of these generalized probabilistic theories that people talk about in quantum foundations these days. Okay, for an HMM, the predictive vector is just a belief state over it's a probability distribution over your hidden states. So your extremal states are just a finite set of points. So actually on the bottom left here, you can think, okay, where does this two simplex come from? It comes from probability over these three things. So there's this natural three-dimensional embedding, but all allowed probability distributions are on that two-dimensional surface with normalized probability. So there's just like you just get some simplex for probability distributions. Okay, if you had a generalized hidden Markov model that corresponds to one of these generalized probability theories where you have some extremal points, you can have like a continuum of extremal points. You can like could have put in another random pure state of certainty there, and then all allowed belief states are in the convex hull of those things. And then it turns out that quantum systems are a special case of these generalized probabilistic theories, which we can think of in terms of GHMMs if we really want to shoehorn it that way. But kind of the point being that these are maybe in hindsight not so much about classical versus quantum, but they're about paradigms of computation and paradigms of representation. And there's the classical paradigm where you have mutually exclusive memories, and then your computational, like your belief states are in some simplex. But if we think, no, we can represent things in a real vector space, then we can take advantage of these alternative structures. And when there are nominal quantum advantages, that often transfers to neural networks. Big caveat though, when you have many quantum subsystems, those compose to have an exponentially large dimension of the joint space, and you do not have that classically. So there's a big difference there. This is maybe nuance for next time. I think maybe I'll kind of end here, although it's an awkward spot, but just to say maybe one more time of the pipeline of what we're finding is that whenever there's some ground truth stochastic process for generating tokens, which in a sense there always is, we just might not know it or know what it is, that ground truth, whatever we're sampling sequences from, it generates token sequences. You train a model on that, you get neural activations. And whatever the ground truth process is, there's some like ground truth belief for how to represent those things well. And it just turns out that there's a linear map from the representation the model generates to this ground truth thing. And that's basically been true in our little examples when you have a GHMM that it's doing these belief updates over the GHMM. Although with this big caveat now of when the world naturally decomposes into many parts, then it's representing these things in orthogonal subspaces. So there's like identifying the parts that they're like intrinsically must be together. Like let's say this two-dimensional thing, I really can't disentangle that. I can't get anything approximately correct unless I allocate some number of dimensions to this. But then for each object that is so tight knit, I'll identify that as an object and I'll allocate a subspace to that thing. That is like the high level story that we are talking about. So anyway, this kind of quantum version of the story is here. Things seem to be universal. And then there's a question of, can this possibly extrapolate? Basically, no, it doesn't seem like it. The world has many parts. There's this exponential dimension advantage for representing it that way. And I think I will close on basically that. So there's some math between tensor product structure and direct sum structure. And I'm going to jump to the end here. Okay. Turns out there's at least part of an answer now for why we aren't on this enlightened path. That the natural geometric embedding of beliefs has this exponential penalty. And so, sure, it might be better in terms of greater fidelity if we could understand the world as one thing and ourselves as part of this greater fabric. But it's kind of untenable. It's so inefficient to represent the world this way that we can't. And maybe more intelligent entities with a lot of resources would represent the world more holistically. But it's also important to recognize that there's an inductive bias for simplicity. And so we'll often just be blind to complexity and correlations in the world because we don't have the capacity for it. So I will end there and thank you guys for sticking around.
Thank you so
That's-
much, Paul.
That's why the monks can just sit on a mountain.
Yeah.
So I felt like it was appropriate. I noticed just as you were wrapping up with your holistic language or your holistic conclusion, there was a rainbow outside.
Nice.
So I think the universe just wanted to emphasize your point. Thank you so much, Paul, for sharing your insight. And let's follow up on a number of questions from Dede. I think that would be really fun.
Sure, that sounds good. Yeah, I think there's a lot to just informally discuss too, and I think I don't know, we'd probably all get a lot out of it.
All right. Any questions, comments before we wrap up for the day?
I'd really like to keep talking about sort of the quantum stuff and
Okay.
Cool. Yeah, that sounds fun.
are you trying to make quantum computers obsolete? I think you should be.
Oh, trying to make them obsolete. Yeah, so there's this interesting point of neural networks can have some of the advantages of quantum systems in that they're using the real vector space. But quantum computers, if they, yeah, I mean, if we can figure out the technologically relevant, yeah, just like the practical aspects of it, do have a unique advantage still in terms of the large dimensionality of the latent space that they have when you put many qubits together.
There's also the fact that quantum representations are going to have a squared advantage when you talk about the linear HMMs that implement the POVMs relative to the actual physical space. You know what I'm talking about, Paul?
I mostly know what you're talking about. It might take some more time to unravel.
Yeah. Basically, a two-dimensional system operates with a four-dimensional matrix when you vectorize it.
Yeah.
So there are certain dimensional advantages there.
Yeah, to the extent that two is meaningful and four is not. It's like I think this is interesting and deep in that it is sometimes unclear to me what is a mathematical advantage and what is a physical advantage.
Yeah.
Well, if you wanted to implement a sort of a quantum computation that has n dimensions and simulate it with a classical neural network, the neural network is going to have n squared dimensions, right?
Uh, yeah.
At least I
I
should say.
guess I was thinking about when we use a quantum computer to model the physical world as opposed to the other things that one might use it for. So if you're going to try and model a physical world, it certainly seems possible that, like, we sort of know that in the classical limit, it doesn't have n squared dimensions, right? Like, our physical reality that we experience is a classical reality. It's not, we're
Mhm.
not, quantum correlations are irrelevant to our lives for the most
Yeah.
part. And so
Yeah.
there's somewhere that that dimensionality starts to drop.
Mhm.
When does it start to drop in a physical system?
Yeah. And it's not just the n versus n squared thing, because what is n in the first place? If you have uh m that's
M qubits?
if you have k qubits, then n is 2 to the k.
Yeah.
So
Yeah.
so that's like, I think the real like n and n squared, like there's some difference, but like the fact that you have um n being 2 to the k in the first place rather than linear in k is the part that feels discordant with our experience of uh, linearly many things. And I actually think there's a really deep connection to this representation in the joint space or factored space, because even for these nominally classical things, we're basically showing that you need an exponentially large representation space just to track correlations. And that's kind of whether or not it's quantum.
Hmm.
And it's just like, well, quantum is about tracking probabilities. So if you want to do it as well as possible, you're in that exponentially large space. Um, but then, yeah, it's really convenient to just talk about how the world is everywhere. Localism, which sounds classical, which is like a factored representation. And then you get this size of the representation that grows linearly. So we've said things that sound quantum and sound classical, but all within classical belief updating and just talking about how we choose to represent beliefs.
Yeah. It seems as if there's, quote, entanglement between parts when you're off manifold.
Yeah, when you're off manifold, there's some correlation. It's not necessarily like a quantum correlation, but if it was quantum, you wouldn't need any bigger space. It's in the same space that like certain types of those correlations may be considered quantum or not, depending on the things that you're representing there.
Yeah. Any closing remarks?
Closing remarks. Closing remark is that we now can and should figure out intelligence, and we're getting there, and it's very exciting.
Thank you, Paul.
So yeah, it was good to see you guys.
Good to see you too.
Have a good rest of the day.
Thanks for the presentation.